All right, so topic 8. So topic 8 is about quality management. In many ways, quality management is closely associated with lean management. And that is partially because as you become leaner, part of the consequences is improved product quality, since part of driving out waste, becoming leaner, also includes increasing the overall quality of your products, and that also comes from your components, what you put into the product. Okay, so with regard to quality management, more formally recognized, there tends to be 8 different quality dimensions. Now, with these quality dimensions, you can think of it as based on various points where you can evaluate. So when you walk into a car dealership, for instance, the most readily apparent indicator of quality tends to be aesthetics. Based on the outside, how attractive does a car look? But even before you visit the dealership, you probably have some sort of preconceived notion of, for instance, Toyotas tend to be dependable, BMWs tend to be performance oriented, and perhaps Hyundais and Kias tend to be more value oriented, or car brands, right? Um, but beyond the aesthetics, beyond the perception, um, part of the reason why dealerships want to get you into sitting in a car to test drive is for you to experience the performance and feature aspect of it, so you can evaluate, the actual product utility of what it is that you're trying to purchase. And beyond performance and features, as you maintain ownership of that same vehicle, you would also tend to experience the reliability and the durability, and finally the serviceability. So, going back to the auto example, uh, if you ever took your Toyota to get an oil change, uh, the oil change tends to be pretty cheap. At an average 19 to $30 oil change with regular oil, conventional oil would be perfectly fine. But on the other hand, if you drive a BMW or Mini Cooper, it tends to require some more specialized equipment. For instance, um, if you get your oil changed at a BMW dealership, you tend to have to spend $120 instead of 20, right? And then finally, the odd duck out here is the conformance quality. Okay, partially because for most of you guys, those products that you purchase where quality is of a very high concern tend to be expensive products that you don't purchase very frequently. And so as a result, you don't buy the same car over and over again. Um, so conformance quality really comes down to something that you purchase very on a frequent basis. For those of you who have ever studied abroad, if you went to a place like India, or if you went to a place like China, or if you did the Pacific Rim um, study abroad trips that include some Southeast Asian countries, there might be days when you really, really miss having good old American hamburgers. And when you walk into a McDonald's, a Big Mac is a Big Mac, no matter where you buy it from. That is conformance quality. How do you make the products uh, to the exact specifications as stated, right? And so, of all of these things, if we were to take it back to process management, conformance quality is where things become very difficult, and it's something that most companies try to study and improve. So moving beyond these 8 qualities, it really comes down to uh, the service element as well. For those, for instance, if you go into a dealership, you can buy a car, but then the dealership wants to keep you coming back for the service. And so what it comes down to is, how do the facilities look? If the facilities don't look very good, you wouldn't want to go there. For those of you who have taken classes in some of the other buildings, you probably know that The Farmer School tends to be one of the best looking buildings on campus, and as a result, you probably enjoy coming to class here at Farmer as opposed to some of the other lesser or rather older buildings that have not been renovated. Reliability, it's something else. We all have our favorite restaurants, but if service becomes a little suspect, we tend to not want to go back. As well as responsiveness. Responsiveness uh, cuts down on time that we have to spend to receive service. This is one of the reasons why, if you look at oil changes, we all think that an oil change is an oil change, and yet why is it that a place like Jiffy Lube can charge $50 for an oil change that some place like, say, Firestone would charge 30? Well, the difference is that you're paying for responsiveness at Jiffy Lube, that they promise to get your oil change done in about 5 to 10 minutes, as opposed to Firestone would keep you there for over an hour. Assurance and empathy. All of these are things that feed directly into that exact time when you received a service. And so all of these tangibles, the reliability, responsiveness, assurance, and empathy, these provide the experiential aspect of a particular service. In sharp contrast, if you look at the product of dimensions of quality, um, these tend to be experienced either before or post purchase that would keep you coming back. By then, you've already spent your money. Whereas with services, a lot of these don't necessarily require you to spend all your money at once. So, for instance, if you sitting in a restaurant that's dingy, that provides you with really bad food, that makes you wait a long time, that your wait staff does not seem to know what they're talking about, and that the manager shows you no empathy when you ask, "Where's my food?" As you sit here, at this point, you can still walk away with no money spent. They'll come out to an empty table, right? In sharp contrast, in order for you to experience reliability, durability, and serviceability, all of these assume that you've already purchased a product and have been using it. Okay. So fast forward a little bit, cost of quality really comes down to either the production process or failure. So so process costs versus outcome costs. Okay. So if you think about a production line, you can try to prevent defects by inspecting supplies. You can appraise your products to prevent costs from escalating. But when you detect a product that's failing, you tend to need to scrap the product to be reworked. Some of them might even be permanently wasted. For those of you who ever purchase something from Amazon, you'll see. Do yourself a favor and just search for the term manufacturing defect. Amazon has a massive number of products that are sold by manufacturers because they're brand new products, but they're sold at a huge discount because there's some sort of manufacturing defects that may not necessarily negatively influence the utility of the product itself, but nonetheless it just doesn't look very good. And of course, external failure is the costliest of all, simply because by then your customers were impacted by the external failure. One of the most widely spread and severe external failures in recent times is the Takata airbag failure. That by the time customers experienced Takata airbags failure, there were fatalities. That as the airbag expanded upon impact, the chemicals used by Takata in their airbag actually sent pieces of metal through the airbag, the shrapnel, and killed the drivers. The shrapnel became deeply embedded in their heads, so that a driver feasibly could have survived that wreck, but was killed by the airbag. So that is one of the most extreme examples of external failure. Some of the other more notable examples include the Ford Pinto truck I'm not sure how many of you guys are familiar with Ford Pinto, but really what it ended up being was the position and the lack of protection for the Ford Pinto's fuel tank made it so that when a truck was rear-ended at 20 to 30 miles an hour, there was a very high likelihood for the truck to simply explode, right? It was later estimated that it would have costed Ford about 2 cents for every dollar it paid out in settlement to fix the failure before it went in customers' hands. So this is an illustration of why it is important for companies to address quality at the source. So you prevent defects from entering your process altogether. You try to appraise your ongoing production to make sure that no defects make it into your final product. And then if you do have defects in your final products, finished goods, you want to make sure you catch it before it flows out to the customer's hand, because by the time it gets to in the customer's hands, you might have to be talking about a class action lawsuit. So why is it that companies don't pursue absolute perfect quality? Part of it has to do with this quality curve. So you can see that initially, as you improve the level of quality, your cost dramatically decreases, partially as a result of minimized external failure cost. But at some point, these two lines cross, that the internal and external failure costs start to drop substantially below prevention appraisal cost. And one of the biggest problem here is that you can never 100% eliminate, you can never fully mitigate internal and external failure costs, but you can spend an indefinite amount of money on your prevention appraisal cost. That is, perfect quality is probably not attainable. And so if we were to extrapolate this curve, you'll see the total cost of quality starts to increase. So this is the inflection point. At this point, this is the absolute lowest total cost of quality per unit, beyond which it starts to increase. And so most companies, of course, they can't 100% ascertain where they're operating along this curve. Some spend a little bit too much on cost of quality, but then they tend to also have marketing dollars to back it up, along with comparable price premiums. But for some companies, they may think that they're somewhere close when they're really pretty far back. The 90s General Motors is one example. When Chrysler briefly merged with Daimler, they actually traveled substantially backwards on cost of quality. So how do you actually improve quality? We have something called statistical variance reduction. Most of you probably have heard of Six Sigma, or some of you may have even heard Lean Six Sigma. But what it really talks about is we're trying to limit the deviation in the products that we produce to be within 6 standard deviations of what we intend to produce. And so let's say that a product is designed to be within about an inch and a half. We want this little spread between an inch to an inch and a half, this half an inch spread, we want it to be able to cover 6 standard deviations of what we target to be about 1 1/4 inch. Now, when it comes to standard deviation, or the variance of our production process, we tend to be able to attribute it into common cause versus special cause. Now, with common cause variation, these are the things that are probably beyond our control, unless we do some wholesale system upgrade, brand new machines. So common cause variations tend to stay. Special cause variations is where we spend most of our time and energy on, because these are the causes that we can identify, that we can address, and that we can reduce in terms of the overall variation. But how do we actually know if we have Six Sigma quality, it begins with something called process capability. So following up with what I said about earlier with the spread example, okay, the way that a company typically does things is that if they want to measure their quality, they would conduct a pilot test. Take a random, the keyword here being random sample, right? Going back to your basic statistics, normal distribution relies on random sampling. If you systematically sample, then you may introduce systematic bias here. So run a pilot test with random sample under actual operating conditions. So if you're a pizza delivery company, you would randomly survey customers about their service experience. If you're a retailer, you would randomly have on a receipt a survey link. Hopefully your customer will take the survey, right? So you run the pilot test under actual operating condition, and then you measure the output against your quality standard. This is what's called process capability ratio. Now, quality standards are generally established by company engineers or process engineers who design the product or service process. And what it usually comprises is that there's some upper specification limit and some lower specification limit. So if you have ever assembled a furniture, you can consider this to be, the width of that hole where a screw is supposed to go in. Beyond a certain width, the screw would not fit at all. It would just strip itself easily. But then, if you have a hole that is much smaller than a specification, then there comes a point when the screw would not even go in. And so really, anything in between the upper and lower specification limit will be considered acceptable. And then the standard deviation will be something that you statistically measure based on your random sample. And so the easy way to interpret this, the absolute value of USL minus LSL divided by 6 statistical, or 6 sample standard deviation, is that your process capability ratio is equal to what is considered to be acceptable divided by the actual process variation. So the process capability ratio is the acceptable deviation versus the actual deviation, hence 6 sigma. So if you have a process capability of less than or equal to 1, in which case anything that's less than or equal to 1 means that your actual deviation is greater than the acceptable deviation, as in it is not acceptable at this point. You would have a process capability, or you would have a process capability ratio of less than 1. On the other hand, if you have a highly capable process, then the ratio will be greater than 1. So again, you see this normal distribution here. It rests on the random sampling assumption. Now, one thing that's missing here, you may be asking yourselves, is what about the mean, right? This process may seem perfectly capable, but let's say that your manufacturing process is systematically making things that are a little too small. Then this entire curve would shift over to the left to the point where you would not be producing something as much over here, but then you'll be producing things that are way too small. So this is why the process capability ratio should be complemented by something else, and that is a measure of the mean. So again, it's the same idea, but after having calculated the process capability ratio, we also further calculate the mean. We account for the mean, where T is your target. That's what you design your average to be. So if you design something to be to have an average about 1 inch, then this will be it. On the other hand, this is your sample average. You take a random sample, you take the average, of that sample. And then you divide this basically the gap between what you intended to produce on average versus what you actually produced on average. And you divide that by basically how much are you allowed to go in either direction. This is the intended average here, intended gap. So again, it's actual gap divided by design gap. So your CPK will be equal, your CPK here, after calculating this process capability ratio from the previous slide, multiplied by 1 minus K, would give you an assessment of whether there's systematic bias. So think about this for a second. If on average you're producing something that you exactly intended to purchase, then the numerator, or sorry, not purchase, if you were manufacturing something that you intended to make, then the numerator here will be 0, and 0 divided by anything 0 would be 0, and 1 minus 0 would be 1, and so your 6 sigma quality would be 1. But on the other hand, if at any time you have a small gap here, if at any time you have T minus mu to be different, that you're producing something that is not exactly what you intended to produce, this term here, 1 minus K, you can think of it as almost a discount for CP. That yes, based on standard deviation, your process capability ratio looks good, but then it must be discounted by the fact that you are not producing exactly up to specification, and that you're systematically biasing. And so as a result, your full capability index, CPK stands for process capability index. Your full capability index accounts for both the deviation-based measure and the mean deviation. Okay, so let's take a quick look at the example here. With the example, suppose that the design engineering team set the specifications to be 10 inches with acceptable tolerances of plus minus half an inch, or rather 0.05 of an inch. So you take a random sample, and the average turns out to be 9.99 inches with a standard deviation 0.015. At this point, I would advise you to pause the video and work on this problem briefly, make an attempt before we proceed. So, based on the calculation, assuming that you did pause and you did try to calculate, the calculation for CP and CPK are as below. So with the process capability ratio itself, you have the upper and lower specification limit, which is plus and minus 0.05 of an inch. It will be 10.05 minus 9.95. That is the acceptable deviation, divided by 6 times 0.015, 0.015 being the standard deviation. And so you have 0.1 divided by 0.09. So without considering 9.99, without considering the mean, your process looks to be capable of 6 sigma quality. But then once you throw the K in, that's your actual mean adjustment, you recognize that your production process somewhat biases a little bit on the low end, 9.99. So you do 10, that's your intended target, 10 minus 9.99 divided by what you designed the process to make. So you get 0.01 divided by 0.05 or 0.2. In turn, you have 1 minus 0.2, so you need to discount your CP by 0.8 because your production is systematically biased to the low end. And so you find out that your CPK, based on just the standard deviation, that should be acceptable because of the mean drifting from 10 to 9.99 is actually not capable. In fact, you are probably making a lot more defects than what your process is otherwise capable of. And so what can you do about this? This is where we're going to a control chart, right? What most companies do is they recognize the target, they recognize there's inherent variability, and then they need to develop a certain level of confidence to make sure that what they statistically observed was not just kind of like a blip on a radar that otherwise doesn't warrant any actions. So control chart tries to keep track of quality performance over time, and in this instance, M&M targets for each bag to contain 24% blue M&Ms, but the actual outcome could be 24.3 or 26, and everything else in between. And so what companies want to do is they want to determine what is their 99.74% confidence, or 3 sigma confidence, in terms of their overall process capability. So what quality control chart basically does is it wants to look at performance over time, where M&M targets 24% on average over time, but they set their confidence limit to be within 3 sigma standard deviation, and so they would accept up to 26.3% as still within reasons, and then 21.7% as being within reasons. But then they keep track of it over time. Again, random samples, statistically measured over time, and then they start to notice that, well, here's one, sample number 6 dipped below the confidence limit. So what this basically tells you then is that for companies, they would allow 3 standard deviations in this to be considered random variations due to normal issues. But then anything beyond, they would attribute to some definable causes. So how do you know if your process is out of control? Well, you look for certain patterns. As I illustrated on an earlier slide, a single point outside the control limits would be considered problematic. But then some other patterns, 2 out of 3 successive points on the same side, so that indicates a potential systematic bias over the period of time. 4 out of 5 successive points are on the same side and farther than 1 standard deviation from it. Again, potential issues. A run of 8 in a row, so you're talking about a trend. Again, you want to take a look at what's happening. And then any consistent or persistent patterns, or any patterns that repeat, that might warrant your attention. So what can you actually do? So quality management is not just statistical, but a lot of it is also managerial. Some of it follows Deming's plan, do, check, act, improvement cycle. We covered this briefly already in the continuous improvement in process management. But this is a systematic way for a company to know what they're doing, to verify that they are doing what they intend to do, and to formally address when things are not going the way they want it to. But beyond this simple plan, there are some other tools. There's the cause and effect diagram. Some people call it the fishbone diagram for obvious reasons. What this diagram excels at is for you to be able to identify major factors that would influence a desired outcome. In this case, you notice a surge in defective parts. So what are the major factors that would contribute? You identify the major factors, and then you start to identify sub-factors. Why can people result in defective parts? Maybe they're not trained well, maybe they're tired. Or perhaps that machines are at fault. Maybe poor maintenance due to poor training. or perhaps it's the material environment. The point with this is it's a systematic way for you to identify all the major and sub factors that would contribute to defective parts, and then as you look at each category, you might be able to group different um, causes of defect with various remedial measures. So, for instance, perhaps if you improve your employee training program, you can both improve machine maintenance and improve people effectiveness, and maybe because people are doing their jobs smarter, better way, just spending less time, so be less tired, or perhaps that machines are not being maintained well because of bad data, or that they're paying attention to wrong measures. The point is, when you formally put down all the different factors, this is how you can actually understand how to go about improving a process. A Pareto diagram is a different way of looking at things. What it does is that once you identify all of these factors, you can actually start to see where are your biggest opportunities. If of all the sub-factors, methods are the ones causing you the most defect, then this represents your lowest hanging fruit, because addressing methodological problem would immediately result in addressing your biggest contributor to defect. People, machines, this is just an example. But a Pareto diagram allows you to identify the biggest causes, the most major causes of defect, and tackle it head on. And so finally, what quality management is intended to convey to you is that with quality management, there is no trade-off between cost versus revenue, but instead, quality management is intended to simultaneously reduce cost and to increase your revenue. Reducing cost because of minimized waste, increasing revenue because of greater customer loyalty. Toyota certainly embraced quality management as a way to become one of the world's most dominant automakers. Same with Honda. In fact, this is the reason why Japanese vehicles are synonymous with dependability and reliability. Okay, and so speaking of Toyota, in your assignment, you will actually get to see Taiichi Ohno himself talking about the Toyota production system and see why it is such a dramatic improvement over the traditional American way of manufacturing automobiles. All right, thank you.